Welcome back. The objectives of this video are to fine-tune our techniques for graphing rational functions. We'll begin by doing a short review of graphing a polynomial function and take a look at the zeros. We will go ahead and graph a rational function, and then we will find a function based on the graph of its function. So let's start here at the beginning in example 1. It says, write an equivalent representation of a polynomial function to analyze the function. Use your findings to sketch the function. So here we have a cubic function. So a third degree function, so we know our end behavior is going to go in opposite directions. And in fact, we know our cubic function is going to look something like this using our leading coefficient test with x cubed. The leading coefficient is positive. We know that our end behavior to the right is going to be to positive infinity and to our left is negative infinity. So we know all that stuff already. So let's go ahead. We want to graph this, but we need to find the zeros. So let's go ahead and factor this function. So we have y equals x times x squared minus 2x minus 15. And that's still factorable. So let's continue to factor that to x times x minus 5 times x plus 3. And that's going to tell us where our zeros are. We're going to have zeros at x equals 0, at negative 3, and at positive 5. So let's go ahead and plot those guys. Zeros at negative 3, at 0, and 1, 2, 3, 4, and 5. And then knowing what our end behavior is going to look like, we know that our right-hand behavior is going to go to positive infinity, and our left-hand end behavior is going to go to negative infinity. And then we're going to just do our changes in direction here, and our graph is going to look something like that. So that's a kind of a look at that particular polynomial function. In example 2, they give us our function here, and they want us to write an equation for the function in factored form and determine if we've got a whole or a vertical asymptote. So let's go ahead and first factor and simplify our function. So our numerator factors our difference of squares to x plus 4 times x minus 4, and then our denominator factors to x minus 4 times x plus 7. So we see here we have a common factor in the numerator and denominator, so we're going to have a whole at 4, and then we have to find the y value of that, so those x minus 4s are going to cancel. We've got a vertical asymptote at x equals negative 7, because x plus 7 can't equal 0, so x can't equal negative 7, so that's where our vertical asymptote is. And then we do have a 0 at x equals negative 4. They don't ask for that. And then find the rest of our whole. That's going to be, that's positive 4. So 4 plus 4 in our numerator, and 4 plus 7 in the denominator. And that's our y coordinate. So 8/11 is the y coordinate of our whole. In example 3, we're given a rational function at the right, and we're going to ask to graph this. And they're going to run us through the process here of what we need to do. Now, some of the stuff we can just look at right away, and we're going to know some things. Hopefully, we know things like, hey, I can eyeball this, and I see we have a y-intercept at negative 2. So 0, negative 2 is our y-intercept, 12 over negative 6. We also have a horizontal asymptote, they might ask us that, based on the x squared over x squared. So that's the highest degree in the numerator and the denominator. That simplifies to 1. So I'll put that down here. So we have a horizontal asymptote at y equals 1. So we can start plotting this stuff right away in our graph. So I've put my horizontal asymptote in, I've put my y-intercept. So before I even factor, there's things I know and can plot on my graph. So let's go ahead and follow our instructions and factor this. So our numerator factors to x plus 4 times x plus 3, and our denominator factors to x minus 2 times x plus 3. So we have a common factor in the numerator and denominator. So we see that here we're going to have a whole at x equals -3. So -3 something is going to be our whole. So those guys are going to cancel. We're going to have a 0 at, using our numerator, we're going to have a 0, x plus 4. So at -4, 0, we're going to have an x-intercept. So we can go ahead and plot that guy. And those intercepts, that x and y intercept, I call those bridges over the x and y axis. I think of the x and y axis as rivers, and the only way to get across a river is to take a bridge, and those intercepts are the bridges. So if we have a bridge, we're going to have to take it. We're going to use those guys. And that's the only place we can cross the x or y intercept. Our vertical asymptote, we can get that from our remaining factor in the denominator, and that's going to occur at x equals 2. So now we can go ahead and let's go ahead and sketch some of this stuff on our graph. So I have put in my vertical asymptote here at x equals 2, and I've started finding the location of my hole. I substitute -3 into my remaining function here. -3 plus 4 over -3 minus 2 is equal to -1/5. So the y coordinate of the hole here is -1/5, and the x coordinate is -3. So we're going to have a hole right here. And now we can go ahead and draw the graph of our function. Using my asymptotic behavior, we'll jump over the hole. We got to pass through that y-intercept, and we're going to head towards the vertical asymptote, and we're going to skim along here and underneath our horizontal asymptote. Now on the other half plane, on the right-hand side of our vertical asymptote, we don't really know where we're going to graph, but it should be pretty obvious. We have no bridges, no intercepts here below or on the x-axis. So there's no way to follow asymptotic behavior from below this horizontal asymptote. So this graph I don't even have to test. I know, because I know asymptotic behavior and I know I have no bridges or intercepts, I have to graph in this quarter plane. And then finally, find the domain of our sketch. Well, the things left out of our domain are the holes. X can't equal -3, and x can't equal 2, but it can equal everything else. So our domain goes from -infinity to -3, and then it goes from -3 to 2, and then it goes from 2 to +infinity, and we'll do the union of those, and that is the domain of our sketch. And finally, in sample 4, we're given the graph of the rational function. We want to write an equation in factored form. So let's take a look at some of the things we've got going on here. We have a vertical asymptote at 2. So we know one of the factors in our denominator is going to be x minus 2. We also have a hole at x equals 4, which means we're going to have a factor of x minus 4 in both the numerator and the denominator. So if we have a hole at x equals 4, we already know we have things like f of x, we're going to have x minus 4 in both the numerator and x minus 4 in the denominator. We already said we're going to have x minus 2 because we've got that vertical asymptote at x equals 2. So those are some of the hints and things we know just right off the bat. With our horizontal asymptote here at 1, that must mean we have a tie in our highest degree numerator and highest degree denominator. So that horizontal asymptote tells us we're going to have some version of x squared over x squared, which is going to simplify to 1. That's where we get that horizontal asymptote. So we're going to have another factor in this numerator of x something, and if we foiled all this together, we would get x squared over x squared. So that's another thing we know already. So the last thing we need to figure out is what this final factor is. So to find out what that final factor is, let's take a closer look at the location of our hole in our graph. We determine that we have a hole at x equals 4, but what's that y-coordinate? We're just going to have to make an estimate here, but it looks like it's right around 3.5. So we have a y of approximately 3.5, or y is equal to 7/2. Which means then that x plus something over x minus 2 has to equal 7/2. Well, we know what x is. X is 4. So we have 4 plus some particular value over 4 minus 2 has to equal 7/2. So what would that have to be? This is going to be 4 plus something over 2. Well, a little arithmetic here. 4 plus what? We need that numerator to become 7, so that has to be 3. So 4 plus 3 is 7 over 2, so that is going to be x plus 3. And we have now figured out our function in factored form. So there we go. We've figured out the function of a graph. We've graphed a rational function, and we'll get some more practice with this when I see you in class.